Hello students, today we are going to discuss the states of matter, an introduction. The three states of matter are solid, liquid and gas. Almost everything we see about us appears to fit neatly into one of these categories. There is one idea that we must understand if we are to appreciate the differences between the three states of matter. It is that the state in which a substance exists is the result of the competition between the intermolecular forces which keep the molecules of the substance together and the thermal energy, which we also call heat energy, which moves them apart. The heat energy, which we also call thermal energy, is a measure of the amount of random movement of molecules. We should not say that heat causes the random movement of molecules, rather the thermal energy is the random movement of molecules. The more thermal energy a substance has, the greater is the tendency for its molecules to be jumbled up, that is, to be more disordered. The most disorderly arrangement that molecules can achieve is in gases. At the other extreme, the most orderly arrangement is in solid. Liquids are somewhere in between. Let's have a look at the molecules of the three states of matter. In solids, as we can see, the thermal energy is low and the molecules are quite well arranged. In gas, which have usually very high thermal energy, the molecules are very chaotic. The random movement of the molecules in liquid lies somewhere between the solids and the gases. The intermolecular forces tend to hold molecules together. There are intermolecular forces between all molecules, but between some they are very weak, whereas between others they are quite strong. When the forces are weak, the molecules are not likely to cling together to make a liquid or a solid unless they have very little thermal energy. The noble gases are excellent examples. For instance, helium. Helium will not liquefy under the temperature is almost as low as minus 269 degrees centigrade or 4 Kelvin. On the other hand, the intermolecular forces between water molecules are very strong. The intermolecular forces tend to bring order to the movements of molecules, whereas heat energy points in the direction of randomness or chaos. Now, whether a substance exists as a solid, liquid, or gas depends on where the balance between these two opposing influences lie. Gas is a state of matter without a definite shape or volume, and the volume of which changes with the change in temperature and pressure. Gases tend to occupy the whole volume of the container they are kept in, as they do not have a boundary like liquids and solids do. Now, since the average distance between the molecules is low, it makes them highly compressible, and therefore their volume decreases with the increase in pressure. The molecules of a gas are in random motion. The average distance between the molecules in gas are large. That's why they have weaker intermolecular forces, which we call van der Waals forces, and the average molecular speed is high. With the increase in temperature, the average speed of the molecules increases and their kinetic energy goes up. There is a definite relationship between the mass, pressure, volume, density, and temperature of the gaseous state. So an equation relating pressure, volume, temperature, and amount of gas is known as equation of state, which we are going to discuss later. Therefore, in measuring volume or amount of the gas, the temperature and the volume should also be specified. Now, there are two standard temperature and pressure conditions normally used to measure the data of gases. The first one is standard temperature and pressure, written in short as STP. It is also known as normal temperature and pressure, denoted by NTP, for which pressure is 1 atmosphere, temperature is 273.15 Kelvin, and the volume of 1 mole of gas is 22.414 liters. The other set of conditions is known as standard ambient temperature and pressure, denoted by SATP, for which the pressure is 1 atmosphere, temperature is 298.15 Kelvin, and the volume of 1 mole of gas is 22.788 liter in these conditions. The pressure of a gas is the pressure exerted by the molecules of the gas on the walls of the container. Now the molecules are numerous in number and the pressure exerted by each molecule is also different, but as a whole, the force applied is uniform. Now the pressure is defined as force applied per unit area. Its SI unit is Pascal, so 1 Pascal is equal to 1 Newton per meter square. Now if we denote pressure by P, force by F and area by A, mathematically we can write that pressure is equal to F by A or pressure is equal to dF by dA. Now let's have a look at the various units of pressure. They are Pascal, bar, atmosphere and torr. So Pascal, which is in short denoted by PA, is equal to 1 Newton per meter square, is equal to 10 raised to minus 5 bar, 9.8692 into 10 raised to minus 6 atmosphere, and 7.5006 into 10 raised to minus 3 torr. Similarly, 1 bar is equal to 100,000 Pascal, 10 raised to 6 dyne per centimeter square, 0.98692 atmosphere, and 750.06 torr. Similarly, 1 atmosphere, which is the most common unit for denoting pressure, is equal to 101,325 Pascal, 1.01325 bar, and 760 torr. And 1 torr is equal to 133.322 Pascal, 1.3332 into 10 raised to minus 3 bar, 1.3158 into 10 raised to minus 3 atmosphere, and is also equal to almost 1 millimeter mercury column in height. Now, atmospheric pressure can also be measured in terms of the height of mercury column. 1 atmosphere is also expressed as 76 centimeter of mercury column, though dimensionally centimeter has the dimensions of length and not pressure. We can find the corresponding pressure from height of mercury column by using the formula P is equal to HTG, where H is the height of the mercury column supported by the barometer, D is the density of mercury, and G is the gravitational acceleration. Now, depending upon the units of H, D, and G, we get pressure in one of its units.